right, so now we're done going over our primers for free Klein-Gordon fields or scalar fields. We've gone over spinor fields now. We haven't gone over all the nuances, obviously. We're going over what the book covers. And now we're going to get into gauge fields or vector fields. Gauge fields, this is going to be probably 5 videos in and of itself. There's a lot of stuff that goes on with gauge fields. And so what I want to do here is really just start off with the Lagrangian, the free Lagrangian for these fields. So let's roll up our sleeves and write this down. So our Lagrangian here, I'm going to do this in black. Our Lagrangian, this is the Proca, P-R-O-K-A, is equal to 1/4, or minus 1/4, F mu nu, F mu nu, plus M squared A mu, A mu. Okay, full disclosure here. We're going to be dealing with a lot of index changes when we work with the Proca Lagrangian and when we work with the Proca equation, because we have these tensors in here. Right? So again, these are our electromagnetic field tensors, these F mu nu objects. But we're going to see when we perform, again, our basic recipe here is you propose some Lagrangian, perform the Euler-Lagrange equations on these things. And then when you perform the Euler-Lagrange equations, you get the equations of motion. So let's see what the equations of motion are for this proposed Lagrangian. But before we do that, we're gonna try to rewrite this in terms of just A mu's, right? So we're gonna try to get rid of our tensors. And in doing that, we're going to try to have everything just in terms of A, okay? So the first thing we're going to want to do is we're going to split this up, right? The F mu nu, this is just, again, 1/4 D mu A nu minus D nu A mu, like this. And then we have D mu A nu minus D nu A mu. And then we have our minus M squared A mu A mu. Okay? So far, so good. Then we're going to want to FOIL this out, right? So we're going to get d mu A nu, d mu A nu minus d mu A nu d nu A mu. So I'm looking here. I'm really just foiling out. You can here. I'll show you what I've done so far. This times this, right, is going to be this, and then this times this is going to be this. And I'm going to keep on going here. This is minus d mu, or d nu A mu, d mu A nu, and then plus d nu a mu, and then d nu a mu minus m squared, or actually plus m squared a mu a nu. Okay. Now what I'm going to do is I'm just going to copy all this, because we're just going to make a slight change in this. Again, a lot of these are dummy indices, so we'll be able to change a lot of these indices at our whim. That's exactly what I'm going to do here. And then I'm just going to re-add our m squared a nu. And what I'm going to do here is really just going to change these guys, right? So I'm going to make that a mu and this a nu. Oh, wait. Yeah. This a nu, make this a nu, make this a mu, and mu, nu, mu, and nu. Again, the reason we're able to do this is because they're really just dummy indices. And then what we're able to realize is that this here is the same as this, and this here is the same as this. So that means these guys are going to cancel, and what we end up getting, or wait, actually, hold on. Do they cancel? What we end up getting is, here, let me just deal with these ones first. The ones I've underlined. We're gonna get 2, we're gonna get minus 1/4 times 2d mu a nu d mu a nu, and then we're going to get minus, oh, this should be a minus sign. That's, or should that be? Because, let me see here. See if that was, so what we're going to get here actually is d mu a nu d nu a mu, and these were supposed to have been minus signs, I believe, when we switched over those dummy indices. Because when we switch over the dummy indices again, we have to take into account, so I'm just taking my jacket off here. We have to take into account the changes in the space-time index. Right, and there's going to be a 2 right there, plus m squared a mu, and so what we get now is, see here, the 2's are going to cancel with the minus 4. And so we're going to get this minus 1/2 d mu a mu d mu a nu minus d mu a nu and d nu a mu plus 1/2. Okay. Again, this sign here, this can be minus or plus. Nothing changed there. The thing that changed was the minus signs here, because the minus sign here because we had to change these dummy indices, and right there also we had to change these dummy indices, and when we change the dummy indices again, we have to take into account our changes in or not the changes, but we have to take into account the sign change when we're doing that, if we're to use the Minkowski metric. So again, this thing was the same as this thing, and this thing was the same as this thing. So that was these that I've underlined here. Okay, we're clear. Now, this is our Proca Lagrangian in terms of just our A's. Now, next is going to be to apply the Euler-Lagrange equations. So the Euler-Lagrange equation, if you recall, again is dl dA rho. Again, this is going to be in terms of A, and I'm just labeling A again with a dummy index. D sigma on dl d d rho A gamma. So again, this is just Euler-Lagrange equation with our A's instead of phi, and yeah, so we want to now put this into here. So we can consider first this term. This is the ugly term. So what's this going to be? So d rho dl d rho dA gamma, or rho. I keep on saying rhos and sigma. I haven't even said sigma, but those are sigmas. This is a sigma. These are rhos like this. I'm saying it all wrong. So what is this? This is going to be d sigma. When we can just look at this term. This term right here. So I will go ahead and copy paste that. And so this is going to be d rho, so all right. So far, we haven't really done much with this. What this is going to look like is, let's see here. So we're gonna, so this here, this right here, we're just really going to do product rule. So d mu a nu. We're going to take the derivative of the other one. So this is going to be d mu a, so what I did here was I'll just say what I'm going to do here. So the derivative of this times this, and then plus the derivative of this times this, right? So that's going to be d mu a nu with respect to d rho a, or d sigma a rho, okay? Plus d mu a nu d mu a nu d sigma a rho. And then all of this times d sigma. Because again, we had that d sigma out here, right here. Okay, there's a lot to this, but I promise once we finish this part, then it's a breeze. Or not a breeze, but it's a lot easier. So next is going to be, we're really just going to break this up now. We're going to say that this is d sigma d mu a nu. And what I'm going to do here is we have, I want to change the index, right? So I'm going to use two matrices here. Okay. And then I'm just going to change the index name. And when I change the index name, I'm going to bring it down. This is the beauty of using our Minkowski metrics, right? We can bring our indices down. We've seen how that works in our previous videos, I think, or in like chapter 2 or chapter, yeah, it was in chapter 2, I think. And then we're going to have plus gamma mu a nu. This one already has lower indices on it, so I'll just keep it as is, because we want everything in lower indices now. So what we're doing, again, is we're bringing everything down in lower indices. All right. Well, now what does this become? Well, this becomes this here. Well, this is just going to be delta sigma k and delta rho gamma, because d y a x is 0, because we're just taking derivatives with respect to the positions along with each orthogonal axis for A. Okay, same thing here. This is going to be mu nu and rho nu. like that. So what I'm going to do is I'm going to come up here and I'm just going to rewrite this as, well, this becomes d rho a rho plus d rho a rho, like this. And you can see how that works, right? Because we're going to have our indices contract with each other. There, there, and then we're going to have indices contract here and here. Let's see, rho and sigma. So we have our sigma, and then we have our sigma rho. So here's our sigma, and here's our rho, and yeah, so we can see how that all worked, right? Okay, I hope that makes sense. There's a lot of index moving around here, which is not very fun when it comes to the Proca equation, but we've now come down to this point where we can now say that this is 2 And the beauty about this now is that now that we've done this, we can kind of understand how this works. If we were to come across this later, we'll just say it's equal to this instead of going through this long derivation, because again, that sort of eats up into time. And that was just the first term, right? So we did that for this. Now we have to do it for this. Now I'm not going to bear you the expense of having to go through that again. I'll just say that for the second term, you get what you get. So this is for first term. And for the second term, you get 2 gamma, or no, 2 d rho d sigma a sigma. Okay. And then last but not least, we have the very last term. We want to take the derivative of this guy here, this one right here, right? And that we're going to use this one, right? Because we don't have derivative terms. This is the potential term, right? If you remember correctly. Or if we remember correctly, this here deals with the kinetic terms. This here deals with the potential terms. This is our potential term. And so what that becomes, it is d m squared a mu. So this was our potential term with respect to dA rho. Well, this is just minus m squared times 2a rho, because this here is essentially a squared, but we need to, again, take into account the change in the sign with the Minkowski metric. And so our overall term, therefore, is that we get minus m squared. Actually, I'll go like this. I'll put the coefficient first. Minus 2m squared a rho is equal to, this is at the product of our Euler Lagrange equation, d mu F mu rho. All right, so this is what we get after putting the pieces together on or the Lagrange equation. This was the potential part. This was the kinetic part. This here, again, I'll go back to the kinetic part, is this here and this here, or this here and this here. Okay, we just took the sigma out, because when we take that sigma out, we can realize we have d sigma a rho, d rho a sigma. Okay, so this is our equation of motion. Now, and recalling that, I just want to recall that sigma and rho go from 0, 1, 2, and 3. Okay. There's a lot to this. And I think I'll stop here for, we've at least gotten to a place where we know what the equation of motion is for our Proca Lagrangian. Again, this is in the free case, no interactions yet. And this is kind of perfect timing. I'm almost coming up here on 30 minutes. But what we could see here, again, there's a couple of things to note, right? There's a couple of things to note. One is that we have a tensor, right? We have a tensor here, and we have a vector here. This looks like we have the gradient of some tensor. So I will actually draw this a little bit more explicitly, because again, what you don't see in the books, in the quantum field theory books, is that hidden behind all of this is, actually I'll write it like this. No, actually I'm good. I'll write it like this. 2m squared a rho is this. You don't, this is suppressed, right? This here is suppressed. And so, but this is a field, right? This is a field. Similarly, this is a field. So this is really what it looks like. But what this seems to suggest, right, is we can write this out more explicitly. We can say that this is d dt. We need, if we're considering general relativity here, we need to put that c in there. F0 rho plus d dx fx rho, and so on. And that all equals a 0 x. Again, I'm suppressing the x mu, but plus a 1 dot 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 times 2m squared. That's what it's like explicitly. We can also write this as, or we can also write this, our Proca equation, this whole equation here, as 0 equals d rho f, not rho, sigma rho x mu plus 2m squared a rho x mu. That's completely fine. Well, fine as well. We're just moving the potential term over. Okay. Also, we can understand that we can ask the question, what if m was 0? Because again, what the Proca equation is going to do is it's going to help us describe, it's a vector, it helps us describe the vectors, or vector fields. But this is going to be important in talking about photons. Photons don't have mass. So if photons don't have mass, then this term goes out. And what we end up with is 0 equals F whoops, I forgot the derivative term in there. D sigma F sigma rho x mu. So this here is the massless version of the Proca equation. It's when m equals 0. Okay. When m equals 0, this is also called the inhomogeneous Maxwell equations. And so I'll write that down here. Inhomogeneous Maxwell equations. We can, maybe I'll put in a Patreon video on how this sort of gives rise to our Maxwell equations. But with that being said, I'm now on about 30 minutes here. We've gone through a lot of the nuts and bolts of this, of the Proca equation. What's to come now is a little talk about solutions to the Proca equation. I'm going to diverge a little bit after we talk about solutions to talk about this dispersion relation. We want to bring that up again, and then we're going to talk about gauge symmetries after that, and then we're going to roll into chapter 6. Chapter 6 is where the interactions start. So with that all said, I will see you guys in the next one.